time. Okay, so we have section 3.3, polynomial and other functions. First thing we need to do is make sure we understand what a polynomial function is. Now, your book gives this really long, drawn-out definition, okay? And it says that a polynomial function in one variable is a function of the form f of x equals some number times some variable to a power, plus some number times some variable to a lower power, plus some number times a variable to the first power, and then your constants. Basically, what they're telling you is that as long as it doesn't have any radicals or any variables in the denominator, as long as the exponents are all whole numbers, like x to the 1, x to the 2, x to the 3, it's considered a polynomial. So technically, lines and quadratics are considered polynomials. Now, today we're just going to look at some higher degree polynomials. Now, the degree of a polynomial is the largest power of x that appears in it. So, for example, if I have y equals 3x to the 5th minus 2x to the 4th plus 7x squared minus 5. What's the degree of that polynomial? 5. It's just your highest power. So we say that's a 5th degree polynomial. And that's how you find the degree of polynomials. You just look at them. And typically we write them in highest power down to lowest power and put the constants on the end. It makes them a little easier for us to work with and to understand them as we kind of go through. So that's basically what a polynomial is. Do we need another minute on that, or are we okay? Good. Okay. Well, now that we kind of know what a polynomial is, we're just going to kind of talk through some of the characteristics of polynomials. These aren't really things that you have to memorize, but the more you know and you look at an equation, the more you know about it, the better off you're going to be when you start trying to find things like the intercepts and trying to graph it. If you kind of know these things, you'll know what it's supposed to look like before you go. So one of the characteristics of a polynomial is that they're smooth and continuous. Now, we haven't worked with anything that's not continuous yet, but at the end of section 3.3, we will get to those. But they're smooth, which basically means this is not a polynomial. It's not smooth. It has a very sharp V to it. A polynomial is more like a quadratic. That is a polynomial. This is a polynomial. But something that looks like this is not a polynomial because there's a sharp turn. There's a weird turn on it that doesn't flow smoothly. All right? So they're smooth and continuous. Do you guys know what continuous means? Maybe you don't. It means that you can trace it from left to right nonstop without picking up your pencil. So everything I've drawn over here is continuous. It's just maybe not smooth. Let's see if we can get a picture that isn't continuous. Let's say we have a parabola here, and then it turns into a line. See how it jumps from there to there? That's actually called a jump discontinuity. It's a break in the graph. And these are piecewise functions. We'll look at them a little later in this chapter, well, maybe even in this section. And we use them a lot in calculus. And so we can like piece together different functions to make something fit a given situation scientifically. So we'll use those, but for now you don't need to worry about them, but that is not continuous. If I trace from here to here, I have to pick my pencil up and come down here. Have you guys ever seen something that looks like this? Y'all know what this is called? It's called a hole in the graph. And holes can show up for lots of different reasons. And once we kind of talk about them a little later on, I'll tell you some of the reasons why maybe you could have a hole in a situation that you're talking about. That's characteristic one. Smooth, continuous, no holes, no breaks, no jumps, just easy to go stuff, no sharp turns. That's what polynomials look like. So your book gave you a few examples as well. So they go, this is smooth and continuous. This one has a cusp to it, so it's kind of a pointy spot on it. That's not a polynomial. And this one has a break in the graph, a jump from here to here. That's not a polynomial either. Is that okay, guys? Okay. The second characteristic is that many polynomial functions have graphs similar to those of lines, parabolas, and cubics. You kind of start to see once you get into the, especially the cubics, you kind of start to see that they're all kind of similar. It just depends how many turning points they have in them. So if your highest power is even, like x squared, x to the fourth, they're going to kind of have the same general shape. For example, this is y equals x squared, correct? Well, x to the fourth is going to kind of look very much the same way. It can either be a wider parabola, or it could be a W, like this, or it could be something a little different like this. But they still have the basic general shape. Both ends go up, or both ends go down. So even functions kind of look alike, you know, and odd functions kind of look alike. When n is odd and greater than 1, the graph has the same general shape as y equals x cubed. We know y equals x cubed looks like this, right? Well, then it could look, you could have one that looks like this, or you could have one that has more than one turn in it like that. Those are all going to be odd-powered functions. So you can tell if it's even or odd based on whether both ends go up, it's even. If one end goes up and one end goes down, it's an odd power or degree. Are you guys okay? As the power becomes larger, they actually get flatter towards the middle, but steeper out on the ends. And you'll kind of just intuitively understand that as we graph. These aren't things you necessarily have to memorize. So remember that. The more familiar you are, though, the easier it will be and the better you will know what to expect when you go into a problem.
And the f of x equals x is just a y.
Yeah, f of x equals x is just y equals x. So it kind of is its own little thing. You know, lines are. But once we get beyond lines, the other polynomials, those you can kind of like draw conclusions about just by looking at them. So we're going to look right here. These are just kind of the very basic x to the 1 through x to the 6th. Just let you look at them. Y equals x is just a line. Y equals x squared is just that parabola. Now let's look at x to the 4th. If you just have y equals 1x to the 4th, it's the same as a parabola, but it's flatter in the middle. But the ends of it are a little steeper. So that's kind of neat. X to the 6th is the same way, but even flatter through here. It hugs that axis for a lot longer before it shoots up. So they just get wider and steeper on the ends. The cubes, this is y equals x cubed. And I can't really see a whole lot of difference between here and here, the x cubed and the x5. What you're supposed to be able to see is that it stays along the axis, the center here, a lot longer than this one does. And the ends are a little steeper. But they basically look the same. Let's take a minute here and see if anybody has any questions. So here's the actual slide that explains to you that the end behavior is the same. Remember when I told you guys that if it's an even power, both sides will either go up or down? But if it's an odd power, one will go up and one will go down, depending on whether it's positive or negative for that highest degree. That's all this slide is trying to tell you there. So you probably already have figured that out by now. So take a look right now at the function y equals x cubed plus x squared minus 2x. And I want everybody to graph this on your graphing calculators. Go type it into y equals x cubed plus x squared minus 2x. And I want you to notice, once you graph that, just click zoom 6. And when you graph it, I want you to notice a few things. Notice that it's very similar to x cubed. You may do something different in the middle, but the beginning and end are the same. And you should be able to see that the graph falls on the far left and rises up on the far right.
Zoom 6.
Zoom 6, yes. So just take a couple of minutes, study that graph. Did everybody's calculator display look like the one on the right over here? Mm-hmm. Well, this is y equals x cubed. If you kind of zoom in on it really closely, this is y equals x cubed plus x squared minus 2x. Adding these other terms over here, just pull the middle up here and down here. So it just makes what we call turning points there in the middle. That's all that happens when we add other terms in. Otherwise, the ends are the same. The far left is the same and the far right is the same. And that's just the way polynomials work.
That's just showing me that they are similar, but not quite.
Right. All right. They can have symmetry. They do not have to have symmetry. And we're not going to spend a lot of time on symmetry. All right? But some of them have symmetry, some of them don't. And you just have to look at your graph and figure it out. Or you have to do the symmetry test, which takes forever. So I'm not going to make a big deal out of that. But every now and then I'll just say, does it have any symmetry? And you should be able to look at the graph and tell whether it does or does not. This is where we really want to get into graphing. And these are the steps we're going to use for graphing. We're going to find any symmetries, and I put that as optional. You only have to do that if you want to. You can always just wait till the end and tell if it's symmetric. Then I want you guys to find the x and y intercepts. That is a definite. You have to find the x and y intercepts, okay? Then you have to figure out where the graph is above and below the axis and plot a few points. These two right here, they can be done by making a table. So you gotta make a table and just put in the values that are around the intercepts. So it's really important that you get the intercepts. And then you just make a table of extra values and plot the points around them.